I guess first is figuring out how you want to do suspension. So you could do a double wishbone, which is what most of us do. There's other options. There's McPherson's strut, which is not really practical for us.
Yeah, I mean double wishbone is kind of like.
Wishbone's good. We're also swing arm, trailing arm.
That's if you have like a single rear wheel. Right?
Oh no, you can do it anywhere. You can do it with fork.
Really?
But it's just instead of double wishbone, it's if I'm looking towards the front of the car, there's a beam that hinges this way and a spring here. So it's a lot
like
simpler.
hard to control like camber and stuff.
Yeah, you have no effect on camera.
That's that, right?
It's not technically the worst. We're actually talking
Really?
about using it on the rear next. Yeah.
What's the benefit?
The benefit's a lot simpler. It's a lot more robust because like there's less.
Like trailing arm?
Yeah, trailing arm, swing arm, do the same thing.
Oh yeah.
It's you mount it in a completely different way. So depending on how you want to view your frame, it might be a better strategy for your mounting.
I guess.
Disadvantages, you don't have as much control of camber gain. As in zero, you take up more of the useful space in your frame for shock. You have a lot less options in terms of like motion ratio, belt crank, shock sizing.
Okay.
So
interesting.
There's multiple types. You probably pick that.
Yeah.
Let's say you go with double wishbone again. Most of the double wishbone geometry is set. The only other really big thing is figuring out your shock setup. Two main things you can do. You can do a push rod, which is it's not under your bottom control arm.
I know
It's pushed. You can do a pull rod. Deciding between those, then you can look at how you want your shock to be integrated in that. Do you want your shock to be directly attached? Do you want a push rod to a ball crank? Do you want, and if so, what does that ball crank look like? Where does it go?
Why do we have push rod in the front but not in the back on this car?
The main reason was because the original design intent of this car was to just go fast, make something fast and simple. And in the simplest design, least moving parts, least things to manufacture, is you just mount your shocks directly. The issue is on the front uprights. We've had a lot of problems with, like you have your axle and that comes off the back of your axle. And typically your shock is aligned with the middle of your upright as well. In the past, we've had issues with.
Wait, you said the axle comes out of the upright?
Yeah, like at the back.
Oh, what?
You have your upright, axle goes this way. There's a little bit on this side.
I have a quiz.
Don't we have like a cap that like?
Yeah, now we do. But before we set it
I have
up.
my midterm for calculus Tuesday as well.
So there's nothing constraining it from.
And then Monday is.
Well, we had it on this side, another side. So it was constrained. The issue is with that thickness.
Oh, the thickness of the nut gets in the way of
On the shock.
Okay.
So we opted for a thinner rod, which is much less likely to interfere.
Basically push rod.
Well, I'm sorry, but can you pick this up? Thank you, bro.
So that's why we went with that this year. The bell crank design was also just stolen from the last car because we were trying to go fast. So,
So on the next car, we could just get rid of the push rods in the front if we use the same cap thing. It's thinner, basically.
maybe. You still have to turn the uprights, and that could still hit the shock if it's big enough.
I see.
But yeah, it's all depending on specifics. It's maybe.
Okay.
But the other thing it gives you to have a bell crank is you can mess with the motion ratio.
Yeah.
Like for like a kinematic thing, the
Wheel shock travel.
yeah, like the shock travel per ankle, you can vary it based on your design. So you can have it a little lighter in the first region and then a little heavier in the second region. So it's like, it thins out vibrations more, but if there's an actual big shock, it'll still catch your car without it breaking, kind of thing.
How would you do that?
Well, you can edit the spring constant. You can essentially change the spring constant if you have some sort of.
Because you can adjust the leverage, like on things.
Yeah, like as you rotate, do you take RMD?
Yeah, but I don't remember last stuff.
It's RMD. It's the RMD material where it's like.
Don't you have to use like a telescopic spring, or like you have to put like multiple springs in series or something to have progressive motion ratio?
Not necessarily. It's
Really?
not based on the actual spring constant. It's based on the relative mechanical advantages and angles of the mechanism.
Remember the graph I showed you earlier?
Yeah.
Yeah, that was like motion ratio stuff.
I see.
So you can edit that if you have a bell crank and you design your mechanism for it basically.
Interesting.
Not necessary, but something to look into if you want it. it'd be cool to have a mechanism, but
So you're saying like as like basically you could just have one shock, but like as the wheel travels up, the actual like K value of the shock.
the relative K value, the
Oh,
value
relative.
that the force that's going into the wheel from the push rod.
Oh, because the
You can
direction of
make
the
it
force is
non-linear.
changing, so the magnitude is like changing.
Yeah, so you can change your
Yeah.
torque on a part, which changes the output force somewhere else, basically.
Okay. Why are you go this
That's pretty much there's a lot of things to think about.
Yeah.
There's simplicity,
Okay.
optimization. You have to find where you think you can sit in the middle.
Why are our ball joints like basically in a vertical line?
Which ones?
Like just like our outboard pickup points basically.
For the control arm mounts?
Like I mean it's not exactly vertical I guess, but like
The ones on the control arms to the frame?
like upright to like control arm to upright connection basically.
Oh, so
Like
those.
here and here. Like it's essentially vertical. It's usually like a lot more like this, right? Like these outboard points.
So you're talking about the one by itself on the end of the control arm, right?
Yeah. Like this is outboard and this is inboard.
Yeah, so the outboard ones, main reason was because on the steering in the front, we didn't want to mess up our calculations and artificially limit our steering angle. It's a little,
Like just for simplicity? Or like
there's a couple reasons. So, right, like the disadvantage of having it go like this is you can knock into the sides, right? So we knew our suspension angle change would be a lot smaller than our turning angle change, probably. So we decided to do that initially. Looking at it now, our wheel only really goes 20 degrees, and there's attachments you can get that are more than 20 degrees, so that isn't really as much of a factor.
in terms of steering?
Yeah, but the main reason is because the way the bolt mounts it into the upright. In the current arrangement, we have the cone spacers, right? And there's,
Like this like the rod end connection?
yeah.
Okay.
So like currently we have,
Oh like this bolt here.
yeah.
Yeah.
So we have cone spacers, right?
Yeah,
So we're
yeah,
just actually compressing them.
Yeah.
Which most things are a lot stronger in that orientation versus if we did it sideways, which is the other nice way to do it, where you have unlimited suspension travel, right? Or kind of unlimited. You're putting that bolt in shear.
Wait,
And
you're saying it would be sideways if this point was like more here?
like if instead of the hole, oh God, where is it? Instead of the hole being on this face, you can put it on these faces. There's like, I don't know what you're asking.
No, I'm asking like what kind of drawing?
You got it.
Like something like upright wheel. Like these 2 points right now they're like basically on a vertical line.
Oh yeah.
Versus like normally they're like this. Right? So why is it like what made us choose it to be on vertical versus like having this point more inwards and this point more outwards?
That was kind of a manufacturing decision, kind of a stock decision, or mostly manufacturing based. So, 2 ways you can do that is you can either start with a really thick piece of metal, and then kind of machine out that bottom part, and then put your mounts further apart laterally, or you can drill your bore hole for the axle at an angle. The first one's really expensive and time consuming. The second one's really hard to get right. Right?
But like machining aside, like just in terms of design, like isn't this a lot better because your scrub radius is like a lot lower, right? Like if it goes here, like it's here versus over here, it's like this much. And so you have a lot more scrub with this like vertical steering axis.
Yeah.
Essentially vertical.
I believe the reason you'd want to avoid that too much, maybe a little bit's fine, but doing that kind of makes it so if you want to turn your car, your steering wheel essentially has to pick up the front of the car a little bit. Because if we're like this, like if our axle is out here,
Mm-hmm.
or are you saying having the axle at an angle? If you're still rotating.
I'm saying like these, like this is the steering axis. So having a steering axis at an angle versus
Yeah.
at like zero.
So if this is your steering axis, this is your axle.
Yeah.
When you're turning along your steering axis, right, you notice the wheel will go down and up.
Yeah.
So,
Bump steer. Wait, is that bump steer? No. That's
I
just,
believe it's, hold on, if it's just in this direction. There is some component of bump steer, one, and it also makes it a lot harder to turn your car. And the point of reducing the curb radius is to make the car easier to turn, right? So this would be kind of having a similar, if you overdid it, it would
yeah, if
create
you
a similar
overdid
problem.
it, yeah.
A
But if you
small
do it like
amount-
a little bit, because
a
that's
small
what
amount's probably
most
good.
cars have this like to some degree, because the reduction in scrub is usually like worth it, I guess,
Yeah.
for like, you know, yeah.
Yeah, you probably could. I think the main reason we didn't was because we, again, wanted to keep it simple. We just wanted to be able to drill at 90 degrees. And
I see.
I think we have a slight offset on the axis, like very small.
Yeah, it looks like there's a slight one.
Yeah, but we didn't really spend a lot of time tuning that, and that's definitely a place that it can be tuned more.
Mm-hmm. Like, yeah, because like I want to like see how the math would be done too. Like if we were to actually like
I'm not sure.
calculate that stuff. Okay.
I've never done it, but there's definitely resources, especially with combustion people.
Yeah, I'm gonna ask them like how they did their math.
Yeah, they have like
On a
a
lot
lot
of
of stuff
stuff.
like too.
Okay, cool. You guys have any other questions? How did we ever do any like analysis between like ride height versus like drag coefficient?
Not really. I believe the correlation is that the higher ride height you have,
You have more lift, basically.
yeah, and which is
Or not drag downforce, yeah, lift versus downforce. Yeah, because like in their CDR they have this thing where okay, yeah, they have this. Is that something that would be useful for us?
Yeah, I know.
Useful for us, or is it,
Well, now I
we don't really care about it?
we don't really care about lift a ton. In theory, we just do our best to have zero. I guess if you're really optimizing, you're making the car with more points. But I'm not sure if your increase in drag would be worth having some lift. CL over CD.
Lift coefficient versus downforce coefficient.
Yeah. Lift versus downforce or drag?
Probably drag actually.
This is lift over drag.
Yeah.
So they're maximizing lift over drag. So I don't believe we do, just because one, we really don't design for down, like when you're creating lift or downforce, you're increasing your drag coefficient typically, which kind of makes sense. Like if you're creating more force, net energy is the same, then you have to be, taking energy from somewhere else, which is typically in the form of more drag. We're not doing that primarily because we don't go super fast around tight corners. We're going at a medium speed around pretty wide corners. So
Yeah,
it's not
yeah,
as big of a
yeah.
design consideration. And we have regs that say this is a minimum ride height, what's the ride height here? Is that in inches?
Yeah.
Yeah, our minimum ride height is 4 inches. So I believe that plot would just like kind of flatten out and we wouldn't see a big change.
What did we?
regardless.
How did we choose our ride height?
Right now it's just a safety factor, as in like, some extra room for margin of error on top of the official lowest. The issues
Oh,
with-
so as low as possible, basically.
as low as possible. The issues with having a higher ride height are it makes you need to have a larger track width if you have a higher ride height, because on our most risky portion of scrutineering is dynamic stability. You have to do a figure 8 test and your car can't flip over. And if you do the math for that, then the higher center of gravity you have, the wider you need your wheels
Yeah,
to
more
be
likely
to
it's a
avoid the
rollover.
flip.
Yeah.
So in general, we want to reduce center of gravity and that kind of just turns into reducing ride height as much as possible because that brings the rest of the car down as much as possible.
Interesting. Okay.
But that's like a dynamic sleeve decision.
Is there a? What was I gonna say? Is there like a 45-degree like tilt test for Stoller?
Yeah.
Oh, there is.
Yeah. So that's just making sure your center of gravity is less than half of your average track width.
Huh.
Yeah.
Okay. Cool.
Which we should barely sneak under if I did the math right.
Oh, this thing. Is this something? So like, I noticed that they calculated like a K value for like their hardware, like shocks or like tab. I think like this is what it's talking about, right? It's like compliance between like the actual hardware, like from like bolts like connections and stuff like that. Like besides the shock.
It's a good idea. Yeah,
It's not something that's important to us. And yeah, if so, like I don't even know how would we measure that?
You can do FEA. You can apply a force and look at the deflection of the part you're
Oh, I
about,
see.
which is probably what they're doing based on the image. I think it's a nice to know, but I also would rather say I'm not sure, or I would say I don't know how much time you would want to devote to this. What's the modified spring value is 10 to the 5th. So that's like a massive spring value. So
Yeah.
And if you really want to optimize performance like they are, then it's probably worth it. And you know, they have background, they're like done with the basic design stuff before school starts to be worth it. For us, it may just be more worth it if you have tunable shocks to
Makes it
do some testing.
Like this
with
is
the IMU data
insignificant compared to
into-
like just tuning.
It's pretty small. It's
Yeah.
so like total spring constant is 500. They're at 10 to the 5th. So, the springs they're using is probably about 20,000 times as compliant as their hardware.
Yeah.
Like this, I honestly kind of feel like this is for their judging.
Oh yeah.
To have this calculation. I don't see this being especially useful unless they're going pretty fast, maybe it is.
Okay.
But for us, I don't think it's useful. At least not if you have other more important things to do. And the way you would compensate for it is you slightly tune your spring, which you can just do based off of the data you get from IMUs.
Okay. Do we know like what current like spring rate / like ride frequency? Yeah.
That's
ride
something
frequency.
I did want to talk about. So we have the air shocks from Fox.
Yeah.
I'm not gonna lie, they kind of suck.
Why?
It's really hard to get data from them. Like most spring, like normal manufactured springs, shocks, they have published and tunable spring values, damping values, preload you can mess with. The Fox stuff is all just kind of like, there's no data anywhere, you don't know what the damping coefficient is, you don't know what the spring constant is, and the spring constant probably isn't even linear inside the region, so it's really hard to do design with it. And testing is also really hard because since it makes heavy use of a damper and the spring, you need a really specialized, really powerful rig to even do that testing, which we haven't had time for. So I'd say in the future, you either want to design a rig that can do the testing and get accurate data, or just buy brand new shocks that are sprung and we can have better prediction on how they behave.
So currently we don't know what the spring constant of our shock is because there's no published data on it.
Yeah.
We don't know what the damping coefficient is. There's no way to measure it.
We have no info on the shocks, basically.
Oh,
We have no info on the shocks.
Okay.
It also changes by temperature, because of course it does.
Like air temperature?
Yeah.
By a lot?
A significant amount.
Damn.
It's measurable.
Okay.
So
So there's nothing we can do to find that?
Is there not like a data sheet or anything like that?
Fox has no hard numbers on their data sheets. It's all like just a graph with no numbers on it.
Oh,
Yeah. Nick and I spent a lot of time looking.
oh no.